I'm very happy to have people from FUDAN. And I started this kind of thing, starvation-driven dispersal. I started this one about 3.5 years ago when I was a visiting professor in East China Normal University in Shanghai. I was there for 6 months. And now we have Shanghai people. And this is so starvation-driven dispersal. This one is for the biological organisms. And if you can read this one. I'm talking about the dispersal or diffusion, which was made by starvation. So if you are hungry, then probably they are trying to find food, so the diffusion will be increased. So that's the point. But if you can also look at this one as an example of a non-uniform random dispersal. I want to talk about dispersal, which is completely random. But randomness does not necessarily mean it's uniform. No, it can be non-uniform. Okay, so we are going to talk about that. So when we say advection, convection in the biological sense, or you can say chemotaxis, then sometimes we think that we know the direction to go. Okay, then that's not exactly random. But this, I want to talk about the random dispersal, but which is not uniform. Okay, and I work okay. So I started this one 3.5 years ago, and now I pretty focused on this project. And I tried. My goal of this talk is to introduce you some of my problems, and there are a lot of related problems I want to let you know. And my hope is to make you interesting about these problems and try to solve this by yourself or with me, either way. Okay, so population dynamics. So that's in the first chapter of the simple OD books. So what's a logistic equation? Okay, this is U is the population. Then usually you have two terms. The first term is the natural growth. The second term, this quadratic term, is a competition term, self-competition. So if the resource is limited, then you have to compete with your own kind for food. Or you can rewrite it in this way, in this way, either way. Okay, probably I will use it in this form. Now in the OD case, okay, we are not that interested in that because that's not PD. I'm PD people. So we want to put migration. Okay, what's migration? They are moving around. So in the survival, migration is essential. If you cannot move around, then you cannot survive. Your species will get extinct. So want to put the migration, then okay, this is a diffusion. So it's a random migration. This one is for the PD model. If you want to patch model, something, okay, there are some patches, they are connected, so they are moving to this patch. That one is called the patch model. Then people may write it in this way. So in here, K is the patch number. So UK is the population at the kth patch. This is a kind of migration rate between two patches. So okay, somehow this one. I'm not talking about the patch mode. I'm going to talk about PD mode. If there's one species, you can write this. If there are many species, then you can use sub-index I. Then okay, somehow you can make things easily. Now let's talk about something very well known. If you use linear diffusion, okay, you have this theory. This theory, very well known. Everybody in that field knows about this. So what they do is, okay, they do competition model. They are two species, and then they have exactly identical logistic population term. Now they have migration of this. Now D1, D2, that's the diffusivity. And U, so reaction term identical, D1, D2 different, so let's say D2 is bigger. Then these two species are identical except the diffusion rate. And let's say let V has a bigger diffusion rate, so we call V faster diffuser, U slower diffuser. And okay, they compete. What will happen? when I thought about this problem for the first time, I thought the faster diffusion will survive, will be advantageous because dispersal is very important. Without migration, you cannot survive. So I thought so, but I was wrong. This V eventually goes to 0, only U survive. Slower one selected and faster one get extinct in this model. So what I thought is, okay, this is something wrong. Okay, many people don't think so, never think so. Okay, many people just say, okay, that's interesting, but I think, okay, that's something wrong. I call that a paradox because we think dispersal is essential, but this one says dispersal will be disappeared in this context. So, okay, this context is not satisfactory at all. Why that happened? So I thought about that. So, okay, probably diffusion is not really the correct diffusion for the biological sense. Biological sense, the diffusion should be a little bit different. Then my idea is now simple. If there's a lot of food in your area, then you just stay there. If you have no food, then you probably want to leave that region to other places to find food. So if there is no food, then their migration rate should be bigger. If there's a lot of food, okay, it should be small. So this kind of non-uniform behavior will make real things. Okay. So what I'm going to do is, okay, so this kind of idea make me involved in the development of the non-uniform random dispersal. And so we can think about several kinds of non-uniform random dispersal. So the first one is what I just talked about, starvation-driven diffusion. Or you can also think about non-uniform random walk. Okay, when you do the random walk, usually walk length, jumping time, that's fixed. But they don't need to be fixed. Right? For example, if you think about this room, we have air, and suppose temperature is different. That side hot, this side is cold. Then even if all the particles are moving in a random way, they are a little bit different. Hot place, they are more active. Cold place, they are less active. It's very similar to the biological situation. There's a lot of food. Okay, you don't need to move around. Just stick there. But if there is no food, you have to move around. It's something very closely related. And to me, they are same things. So applications. This kind of thing started with the mathematical ecology problem. However, you can also apply this on chemotext theory. Or more interesting, what I really want to try is to use this kind of idea to resolve some issues in thermal diffusion. I don't know if you somebody familiar with thermal diffusion or not. So, but this talk is more focused on the starvation-driven diffusion. It's more related to the mathematical ecology or biology. So, the diffusion I'm going to use is this kind of diffusion. It's gamma. So, gamma is a function of probably U and M. So M is the amount of the food. In some sense, U is your population. And if this gamma, so you may think this gamma is kind of a departing probability. Okay? If you don't like this place, you want to depart, then gamma should be bigger. You like that place, gamma small. So if this gamma has this kind of property, it's increasing with respect to U, decreasing with respect to M. Okay, that means there are more population, you want to leave. There are more food, then you want to stay. Then if this gamma satisfies this one, probably we can call this one is a starvation-driven diffusion. Now I want to introduce you starvation measure, something like this. Okay, so as U over M, so if U is large, population is large, then you starve, right? If M is large, a lot of food, you are not starved, right? So somehow this one, some sense measure how you starve. If there's a large number, you're in a bad situation. So if this gamma is just a function of S, and if this is increasing function, then you can easily check that gamma derivative with respect to U is then derivative S, derivative inside, then this positive, that's negative. So definitely this one is starvation-driven diffusion. And the next one is, okay, if you have a gamma, what should be my function gamma? So probably, okay, this kind of function. If S is less than S star, L means low. If S is bigger than some critical value S star, then high. It's a bigger value. In this case, then definitely this is increasing function. But okay, I like this function because this one has very sharp discontinuity. That's very nice. However, sometimes it's difficult to handle that. Then I can use its regularization. And you can call this S star kind of a jumping moment. So okay, you are starving, but you wait a little bit. Now, if you are too starved, probably you have to decide to leave. So this S star is the critical value. Okay, so that's the now application of this starvation-driven diffusion to competition model. So okay. And somehow I thought that a lot of things are done using just a linear diffusion. Now I'm trying to think about some other kind of diffusion. Now if this other kind of diffusion makes sense, then a lot of things will be changed. A lot of theories, a lot of models, a lot of examples will be changed. So that's why I'm very focused on this one. And I'm trying to use this one in a lot of places. And try to, my purpose is to make people to look at it and then use this kind of idea. And this one is the first example of the competition model. So in the competition model, okay, it stays this one. This one is the same, but for the second one, I replace this diffusion with the starvation diffusion, driven diffusion, and make them compete. Okay, and in this context, there are two species. Then, okay, my starvation measure is this: total population divided by m. Of course, here m is a function of space x. Now this is not constant function. So if m is constant, okay, it does not. The theory is not that interesting. The important thing is s is not constant. Then this is somehow starvation thing. Now, if you use this one, your S, then if you rewrite this diffusion, then you can rewrite it in these forms. Right? Use the product rule and the chain rule. Then you will get these things. Then you can see that what's this? This one is just a regular, look like a regular diffusion. And this one look like a kind of a self-diffusion. This one look like cross diffusion. This one look like advection toward more food. I'm ready for you. I didn't just want to interrupt your picture. Okay. So this one is starvation-driven diffusion. Even if you look this one simple, if you rewrite this one have a lot of things, and all these terms make things a lot different. Now I want to compare this one something called some diffusion model suggested by Shigesada, Kawasaki, and Teramoto many years ago, and many people use this model, and somehow they put this kind of thing in front of V. Now they write that, and they call this one regular diffusion. This term cross diffusion. This one self diffusion. If you rewrite in this form, then you get this one. So this one corresponds to this. This one corresponds to this. Corresponds to this. So basically, this one corresponds to these two. This one corresponds to that, but this one has no advection term. Now, a lot of people, there are many papers related to this, but what I believe is basically this one has no physics, but this one has some reasoning why we should have this. Okay, so I believe this one is much better than this one, and this one will give you a lot better theory than this one gives you. So I say, okay, many people do the cross diffusion theory based on this one. Okay, I suggest you, why don't you try this? Okay, so now I want to introduce some of my papers related to this kind of thing. So I never go to details. So the first paper related to this one is a kind of introducing the model, what's the idea, and the examples of the some biological organisms that gives you starvation-driven diffusion. So Unju Cho is a biologist, and myself, and then this is probably our first paper related to this issue. And in this paper, we are talking about some biological examples and comparison with other traditional models. And we had only numerical simulations, no mathematical analysis in that paper, and then some discussions about the model and the possibilities, all these things. So if you check this kind of paper, probably you will get good idea what I'm talking about. And the second paper is with Kwon and Fang Li, and they were postdoctor at that time at the East China Normal University, the PD Center. And this paper is for the single equation case, no competition, but just one single equation cases. And then somehow we showed some non-zero steady state driven by starvation-driven diffusion only. So that means even without this reaction term, you may have some non-constant steady state. I think that's very important. Why? Sometimes, okay, so if you look at the city, there are a lot of people. In the countryside, there are less people. Why is that? There are two theories. One theory is, okay, in the city people, they have a lot of babies, so that's why there are more people in city. But you don't agree. That's why you laugh. So probably the reason why there are more people here is a lot of people living other side moved in. So this kind of non-uniform distribution is made by migration, not the reaction. So usually the more important, the pattern should be made by this one, but not that. But all the previous theory, if you use a linear diffusion here, okay, this linear diffusion does not give you any pattern, right? This is a Laplacian of u equals 0. Everything is constant. So when people do the equation with the linear diffusion with the reaction term, okay, they can obtain some pattern, but that pattern is by the reaction, not the diffusion. But now here, this migration will give you some pattern. So that's the difference. Non-zero steady state driven by starvation-driven diffusion. And then we also obtain some global asymptotic stability. So whatever your initial values, you always converge to the steady state. And optimal selection property. So if, basically this one says if gamma is sharply discontinuous, and a ratio of H and L, high dispersal rate, low dispersal. If that ratio is bigger than the ratio of maximum of M and minimum of M, then you will get steady state such that U is exactly M. So that's we call this optimal selection property. So okay. So basically, this paper is for the single equation case. The third paper is competition. One example is, okay, put the linear diffusion here. Here is the starvation-driven diffusion, make them compete. Then you can see that there is some selection toward the fitness. So if you use the linear diffusion model I introduced you in the first slide, which is done by most of other people, that one says that the slow one is selected. So they are talking about only the size of the diffusion. Okay, what else? Since their coefficient is diffusivity only, so that they have only size comparison. But here, it's a little bit different. You have more parameters. You can now talk about the fitness. What's fitness? Fitness means somehow if there is some resource distribution, then somehow that dispersal gives you some property that the population, make the population fit the resource distribution. So that's a kind of fitness property. So if you have better fitness property, then you will be selected. So in this case, if this one has a better fitness property than this one is, then V is selected. So somehow I think the result of the theory is make more sense than the traditional models. So that's why somehow this kind of idea is promising in this kind of field. This is paper number 4. And related to this competition model, and this one was just submitted actually 2 days ago. Now the idea is this. Okay, it's the same reaction term. Now here, both of them kind of starvation-driven diffusion, but this one is starvation measure S1. This is starvation measure S2. They are using different starvation measure. Now, you can think about the 3 kinds. So we thought about 3 kinds. What starvation measure? First one is S0. That means constant. So actually they don't measure the starvation, just they think constant. So in that case, it returns to the previous, the linear diffusion case. Or this one measures, think that starvation is U over M only. So that means they count their own species only, not other species, their own species only. But that's not exactly correct. Now this one measures the total population of my species, other species, or all species, and then divided by M. Some sense, in some way, this one is very reasonable to assume that species measure this. Why? This is total population, and this one is amount of resource. So if you flip it, then that's the amount of food you can obtain, right? So many cases, you don't care what's the total population in this city. You don't care what's the total amount of the resource of this city. You only care what you get every day, right? So there's something that's also somehow that's the correct quantity. So here the idea is if they have measured things in a different way, and if gamma is precisely the best one, then okay, that's not that interesting. But if gamma, for example, we consider the jumping time S star B. Jumping time is S star. Now, in the context of the local volatile competition model, the resource is fixed. So M is fixed. So if this one is bigger than 1, then this becomes negative and population is decreasing. If this one is less than 1, then this part it becomes positive, then population is increasing. So somehow if S is bigger than 1, then you better to leave because there's not enough food. So S star equal 1 is is the best choice in this context. However, if you choose S star B not 0, then many things may happen. Sometimes one of 2 species is selected, sometimes 2 species coexist, and you can observe some kind of bistability, and then okay, you can also obtain, some cases you can obtain global asymptotic stability, and then also we did some stability analysis related to this one. But basically the analysis is more complicated. So many cases we can use the traditional technique to this problem. But that's not good enough. But that may handle many parts of it, but not completely. So in some sense that's good because you can at least do something, use all the technique. Now there's also some room that you can extend or develop the technique. So that's a good thing. And then I think I better to go a little bit faster. And the further questions. You saw that using that simple idea, there are many things you can do. Actually, we did many Already we wrote 5-6 papers related to that. But there are a lot more things you can think about, right? It's okay. You change your diffusion. And if you believe your diffusion makes more sense than other things, then you can find really a lot of things. So you can apply this kind of idea to the prey-predator models. Then you may also ask, what is the best jumping time? If there is no temporal change of the environment, then probably S star be 1. But if there is a fluctuation of food, then when you should leave, sometimes better to wait a little bit, even if you're hungry. But sometimes you have to leave. When is the best time? So this kind of question is probably makes sense in ecology. As an ecology problem. Then we can do also some patchy problems. Now, in this kind of problem, there is some computational challenge. If you consider two-dimensional case with some domain, and you put the reaction diffusion system, then in this case, the gamma may have a strong nonlinearity, and this gamma may have a singularity at sharp singularity. And computation was not easy. Now also we wanted to compute for a very long time, so it's even challenge. So in the numerical computation, we just did the not PD model, OD model, so patch model. We make some computation for PD. Now for this kind of computation is important. I think the reason is the pattern formation. So reaction diffusion case, people study a lot of things related to the Turing instability, some pattern formation for these things. Now, if you change the diffusion with this kind of form, I believe you will get a lot better things. But it's a lot more difficult to the computation. Now, another application is traveling chemotaxis. So what's the Keller-Segal model? Keller-Segal model is this kind of system. Now U is a population, M is kind of a food. Previously, that food was carrying capacity. This one is not the carrying capacity, really a food. If you eat, this disappears. Eat, that disappears, and then this one is a diffusion term, and this is a chemotactic term. And the basic idea, their basic idea is small bacteria. They can sense the gradient of the chemicals. So that's why they put this one. Okay, my idea, simple. Okay, forget about the gradient sensing. Just replace diffusion. Just replace the diffusion with this kind of starvation diffusion. Then if you rewrite this, so this one means, okay, this one does not assume the gradient sensing, but if you rewrite this one, then you get some advection term. Okay, so I thought this one is good enough to explain chemotaxis phenomena. So in our fifth paper with my student Chang-Yun, okay, what is this? Okay, use that model and then just redo or obtain all the traveling wave in the so the traveling waves obtained by other theorem can be recovered completely using this model. So the point is, okay, this model really explains the traveling wave phenomena very, very well. So somehow this one is the kind of traveling wave. Or so this one is a kind of a peak type traveling wave. So this one is front type traveling wave. This is peak type, but it's not finite mass. This peak type, but not finite mass. Okay, now, okay, let's go. Okay, it's time. I will just finish it. So, random diffusion. So, we're using some Brownian particles. So, okay, this one is more related to the thermal diffusion idea. Then Einstein's relation gives you some connection between random walk and the diffusion. But in this case, when it's the case when delta x, delta t, they are all constant. Temperature is constant. If temperature is not constant, okay, if temperature is not constant, then delta x, delta t probabilities, they are not constant. So this d is not constant. So Fick's law says, okay, this d is here, but I don't think so. This is the correct equation. Somehow, why is okay? So somehow this is we can do some Monte Carlo simulation. So set dx, pick some domain, and each places fix delta x, delta t, and then do the simulation. Then this is theoretical steady state obtained by this equation. And then you can easily see that, so they really converge to this steady state. How many? 10 million particles, 1 million particles. Then somehow, really this one explains non-uniform random walk. Now, random walk, so this is the last one. Sometimes we want to consider, so if you are a living organism, the distance. Okay, you don't probably, in many cases, bacteria don't care about the, they do care about the Euclidean distance. But if food is related, some distance related to food is more important. So in you and me, if there's a lot of food, then probably you don't need to wait for me because there are too many food, so distance is very long. And if there is no food between you and me, then probably there's no food. Then I probably easily go to your place to find the food. So if M is the distribution of food, then this kind of metric is more relevant, can be more relevant to the biological organisms. And if you use this distance, and if you consider random walk, then this is your random walk. Then, okay, you can rewrite that. You have this kind of advection, this kind of diffusion. Multi-decays, you can also consider this one. And yes, this one is exactly the equation of Laplace-Beltrami operator. And then we talk about it. But the case, if one decays, they are same. Multi-D, they are different. Okay, he's sleeping, but he gave me good explanation about the Laplace-Beltrami operator. So what I did is, okay, use this operator here. Now instead of the starvation-driven diffusion, I put this one, this kind of diffusion there, and then try to recover all the traveling wave again, one more time. Okay, that's what we are doing. We are almost done. So that's another paper with Sono Choi, and Sono Choi is he's a collaborator of him, and also he's a postdoc here, so he's working on this kind of problem. And then this one also gives you traveling wave correctly. And I think that's it. Thank you.